This is, what, 2 again, right? So 2 natural log 2. And then right here, minus natural log 3. Let's clean this answer up. This is negative natural log 2, and then distribute through minus 2 natural log 2, and then plus natural log 3. Can I do any more cleaning up here? These two can come together to give me how many of them? Negative 3 natural logs of 2 plus natural log of 3. Can I do anything else? We can combine the natural logs. Let me try this, see if you go for this. Do you agree with that? Just change the order. Right? Yes? Do you agree with this? Where'd that come from? The 3 came up as a power on the 2. 2 cubed is 8. What did I do there? If you have 2 logs, right, being subtracted, you can turn it into a single log with division. So you might want to go review properties of logs. If this seems kind of like, what? I'm using this property right here. My guess is that's probably on your sheet somewhere too. Let me see if they give you properties of logs. Hey, what do you know? That's reference page 4, Laws of Logarithms, property number 2. Except they use an arbitrary log. They use log base A of x over y equals log base A of x minus log base A of y. That's the formula in your formula sheet. Is a natural log a log? Yes? It's log base E. So when you have log base E, that's the natural log. All right, so that would probably be the answer that would appear in the back of the book for that. All right, everybody happy? The way you feel right now. No, no, I'm defining happy to be the way you feel right now. That's happiness. That means you'll be elated later, right? All right, we ready to be done with this for now? I really have not come up with a good homework assignment for this because, you know, we've done so much integration now, and I told you to skip all the ones with the numbers. You know, so I mean, if you really want to practice this, I would say just go back and go through your homework. In each section, pick, you know, 2 or 3 problems that you've already done. Take that antiderivative that you had and try plugging in the numbers now at the end. And that would be how you could prepare for this a little bit. Does that make sense, what I'm suggesting?
Yes.
Okay. So we're going to move into the last section. We only have 20 minutes, but it's enough time for me to introduce you to it. And what are called improper integrals. These are integrals that just kind of, they're improper. They don't They don't behave well. They say the wrong thing at the wrong time. Socially awkward, kind of. Now, what's an improper integral? We actually have two types. Okay, so when we refer to what are called improper integrals, there's a type 1 and a type 2. We'll spend a little bit of today on type 1. We'll finish off type 1 next class. We'll get into type 2 next class. And then probably next Tuesday, we'll wrap it all up and then talk a little bit about the test, and then you'll have your test. This will be on it, though. I have placed all the videos for the homework assignment. For this section, they're already up on YouTube. I finished the whole assignment today. So you have access to all the odd problem solutions worked out. All right, so we're going to talk about type 1. Okay, type 1 are called infinite intervals. So what we've seen so far, and it's not really like we spent a lot of time on this. We've only spent maybe a day on the concept of the antiderivative and the fundamental theorem of calculus somehow giving us the area underneath a curve between 2 points, right? Between A and B. What we're going to do now is we're not going to restrict ourselves to a finite interval. We're actually going to let the interval become infinite. So instead of saying, okay, stop at B, I'm going to say don't stop and find the area. And that may seem kind of weird because you may be saying, well, there's going to be an infinite area then, right? I mean, if you're going to keep this function going forever and never stop it, then ask me to get the area, then it's probably going to be an infinite number. But if the function behaves properly, then sometimes that area is finite. So let's look at this right here. It says anytime we have an integral where your limits of integration go from A and never stop, so to say that I go to infinity, or instead I go out to the left infinitely, which would mean negative infinity to, what do I use there, B? Yeah. B, or if your integrals have an infinity on both ends, then these three sorts of integrals are type 1 infinite intervals. So here's some pictures, just to show you a picture. This is an example of where you're trying to find the area here between 1 all the way out and you never stop. Now, does it appear to you that that function has an asymptote? Right? It's going towards the x-axis, getting smaller as you go. But it never actually gets there, does it? So does it make sense for me to actually talk about the area from 1 out forever? And is that number finite? Well, we'll have to figure that out. Sometimes it will be finite, sometimes it won't. Here's the other direction. You have a function, and you're stopping on the right side, you're actually stopping, but out the left side, you never stop. That would be this case. And then you could have a combination of both, which would be something like this, where you have a function that you go out both ends forever, right? Both ends forever, and you try and look at the area, and that would be this type. I'm sorry, they're all the same type, but that's what the integrals would look like. And these right here are of particular interest. These are used a lot in statistics. Anybody that's ever heard of a bell curve, right? Heard of the bell curve? Standard normal bell curve? I think I may have mentioned this in the very beginning of class. But when you have a bell curve, it looks like that, doesn't it? If you take 1,000 men and you measure how tall they are, right? You're going to get some average, right? You're going to get like the average height. You're going to have a lot of men that lie in a certain window, and then they're either going to be really tall or really short. But as you move out to the sides, the number of men that are really tall goes down, right? And the number of men that are really short goes down. So both ends of the curve get smaller as you go out to the side. That's a standard normal bell curve. Well, in statistics and probability, what we want is a function that when you look at it and you take the area in both directions forever, okay, the area infinitely, you want that area to be 1. If you can find me a function that does that, where you go both directions forever and you get a total area underneath that function of 1, then you've created what's called a probability density function. And they're very valuable because if the area is 1, then I can look at the height of this right here as the probability that a person would, let's say, be this tall. That's the height. So however tall this function is. But when you talk about probabilities of events occurring, have you all heard from statistics that the total sum of all probabilities has to be 1? No? How many of you taken a stats class? Anyone here no one's taken a stats class? Oh, I should just shut up then. Nobody's taken a stats task where you flip to the back, stats class where you flip to the back of the book and you look at a table? No? Okay. Well, then you don't know what I'm talking about. I'm sorry. It doesn't help if you haven't seen it, but think about it. You know, if you have a standard 6-sided die, right? Right. If you have a die, you roll the die, right? There's so many different ways that this could happen. You could have a 1, you could have a 2, a 3, 4, and a 5, and a 6, right? What's the probability of each one happening? 1/6, right? 1/6. So if I measure this, say that's a rectangle, 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 that's a rectangle. And let's say the width of each of these rectangles is 1, right? Then the area of this rectangle is 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. If you add all those up, you get what? 1. That's what a probability density function needs to do. The sum of all the probabilities has to add up to be 1. But see, the thing about rolling a die is that the values that can come out are finite. I mean, are discrete, what we call discrete. You can't get 1.5 when you roll a die, right? But not everything is discrete. When you measure people, it doesn't have to be exactly, you know, so many inches. You can have decimals, can't you? So you can have all the numbers in between. And if you include all the numbers in between, this no longer looks like a bunch of rectangles. It looks like a smooth, continuous curve. And then you want the area underneath to, again, add up to be 1. And that's where this whole thing with what we're doing here comes into play. So, all right. I think I've stretched out further than I can here. You just have to trust that these type 1 indefinite integrals, or infinite intervals, right, these improper things, are very useful. Very, very useful. Okay, so how do we handle these? How do we handle these type 1 integrals? So I think what I'll do is I'll start with an example, and then I'll refer back to the notes. It's easier if I do it that way. So let's take a look at the integral from 1 to infinity of 1 over x squared dx. What I like to do when I'm doing these improper integrals is first just draw a number line and then put my I'm going from 1 to infinity, right? So I'm going 1 out this direction forever. All right? Then what I'm going to do after I draw my little kind of interval of where I'm going to be is I like to get an idea of whether or not this function has any discontinuities, whether or not the function has places where the function is undefined. Does this have a place where it's undefined? At 0, right? We have discontinuity at 0. Is 0 in here? Right? 0 is over here, right? I'm not looking over here. I'm looking over here somewhere. So I'm checking that. And the reason why you need to check it is because the type 2 improper integral is when this is 0, or when the bottom is discontinuous, or the function is discontinuous. And that lies in our interval. How do we handle that? So we look, there's our interval, the discontinuity out here at 0, I don't have to consider. All right, so here's the standard setup. What we're going to do is we're going to take a limit. Just write this down, we'll talk about it. If I don't put this limit here, right? If I don't put that limit right there, what does that represent? Geometrically, what is that? Geometrically, what does that represent? The area underneath that curve from 1 to t. And t would stop somewhere, right? So what I want to do is figure out what that turns out to be, and then let t go to infinity. That means let that thing go out. Let that t where I stopped, just let it go. And that'll take off to infinity. Does that make sense? So that's the idea. It's like we're stopping it at t to get an answer, and then we're letting t go out to infinity. All right. This equals, so you need the antiderivative of that, right? Right, you need the antiderivative of that. Also, the limit we have not taken, right? The limit is going to come in at the very end of the problem. We're going to actually take the limit. So the limit's got to come with us. And now you need the antiderivative of this. So what is it? Negative 1 over x. Is that what I heard? That is the antiderivative of this. Because that's really x to the negative 2, and then you add 1, and then 1 over that, and you get this. That's the antiderivative. I have to evaluate that antiderivative where? 1 and t. Okay, so let me kind of highlight things here. This piece right here turns into this piece right here because of the fundamental theorem of calculus, right? Like if that limit wasn't there, right, that red piece means this red piece, yes? Because of that. And what am I supposed to do with this? Plug in, right? Plug in the 2 points, and then the limit is still out front. So I get limit. T is going to go to infinity, but not yet. Of, I plug in t, then I plug in 1, I subtract the 2, right? So I'm going to set up my 2 sets of parentheses here again. But notice that those 2 sets of parentheses are living inside of the bigger parentheses because I still have to take a limit. What happens if I plug t in for x? Negative 1 over t. That's it. What happens if I plug 1 in for x here? Negative 1. And now, let t go to infinity. Right? We've done the plugging in. We have an expression. There's t. Let t go to infinity. What happens when you have a number like 1 and you divide it by a number that gets huge? Gets smaller, right? That gets smaller? So this piece goes to what? 0. See, no more limit because I'm actually letting t go to infinity. That goes to 0. This right here, there's no t in it, right? So this is just plus 1, which is 1. The answer is 1. So let's just discuss geometrically real quick what this is saying. If you were to graph 1 over x squared, so you get on your little graphing calculator and you graph it, 1 over x squared is the function. If I went out to 1, where would I be on that function? If I plug in 1, where would I be? 1. Up at 1, right? Where would I be if I plug in 2? 1/4, right? If I plug in 3, I'd be at 1/9, right? And so as I go out, this thing is diving down towards 0, and it's going pretty fast, right? It never gets to 0. Never. So if I were to take this asymptotic function and I were to look and try and compute the area under this thing forever, what I can tell you is that that area converges to 1. That means it gets very, 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 very close to 1. That does not mean it is 1, because if you ever stop, if you ever go out here to, like, you go to 1,000 and you actually replace your t with 1,000, you will get a number and it will not be 1. It'll be really close to 1. If you go out to 1 billion, you plug 1 billion in here, you're going to get a really, really, well, the number is going to be really, really close to 1 again. It won't actually ever be there. If there was some way that you could go forever, then you would theoretically have an area of 1. Does that make sense? That's why we use this term converges to 1. So what we're going to see next class is that if we do this limit and we get something that's not finite, like let's just say that this, instead of this, was t, and I let t go to infinity, this piece would become what? Infinite. And then what we would say is that the whole area blows up. And so this integral, the answer would not be infinity. The answer would be, instead of converges, we would say the integral diverges. So that's what we really are trying to get to with these improper integrals. Does the integral converge? If so, what number does it converge to? Or does the integral diverge? Can we start a sign-in sheet? Or wait, everyone took the quiz? Everyone took the quiz, right? No one skipped it? OK, I'll take it off the bat. I want you to think about this. You can start packing up. But I wanted to see what you thought of this. What do you think that's going to do? Think it'll be 0? What does cosine look like? Like this? What do y'all think? How many think 0? Anyone think anything other than 0?
If you define it, you have a domain restriction, it should be.
So look, I said you could pack up, but please give me your attention, okay? If you were to actually just go out to 2 pi, we showed that the area right there would be 0, wouldn't it? But if I stopped a little bit past 2 pi, would it be 0 anymore? No. Okay, if I stopped like right there, would it be 0 anymore? No. It's only going to be 0 at multiples of 2 pi, isn't it? Yeah. So if you're going to infinity, how can you say it's 0? Because as you move on, like, yes, you will. If you think about like accumulating the area, like right here I have some area, right? Positive area, and then it's probably still positive, and then at some point it counters it and it becomes 0, doesn't it? And then it's like positive, a little negative, now 0, then positive. And so as you move on, the area behind you is changing, isn't it? As you move across, the area is actually fluctuating. In the last problem, this, as I went out, the area behind me just kept getting smaller and smaller and smaller, right? I mean, as I moved out, every single time behind me the function was collapsing down to 0. This function's not collapsing behind me. It keeps oscillating back and forth. So do you think it converges? Do you think it actually goes to a number then, the area? Yes or no? Do you think it goes to a number? Probably not. Probably not. So in the case that it does not, we say it diverges. So this is actually this would actually diverge.
For every multiple of 2 pi, it converges at 0.
Well, no, because convergence requires that we don't just pick certain places. You could say that integral, right, this integral, let's call it k, is equal to 0 whenever k is this, this, this. But if you change it to infinity, it's either going to converge or diverge. It's one or the other. Okay, homework. What's your homework? I'm not sure we're ready to start anything on this. Let me tell you what it's going to be so you can at least have this. It's going to be 6, it's going to be off of page 360. It's going to be 5 through 31 odds. And you could do number 5 and number 6, even though I didn't assign 6. You could do number 5 and 6 and 8 and 9 right now if you want to try and get ahead. 5, 6, 8, 9. If not, get caught up. I know a lot of you said you still weren't done with the partial fraction homework. Get that done. See you on Thursday. Yes? Improper integrals will be on the exam.
Sir, I have a question.
Okay, let me turn my recording off.
Sure.